Good afternoon to all of you. I am Dr. Gaurav Saxena, Associate Professor in EC Department. Today I have discussed the magnetostatic field. This is the first I just showed to you what is the Maxwell equation. So Maxwell equation in differential form and integral form, which is very important. So first Maxwell equation is del dot D is equal to rho V, and d dot ds is equal to rho v and rho v into dv. So this equation is also known as Gauss law. In the Gauss law, so total outward flux, which one is equal to the volume charge density at a particular time. And the second Maxwell equation is del dot b is equal to 0. Or in the integral form, we have to be derived that b dot ds is equal to 0. That means what is the meaning of this? The non-existence of the magnetic monopole. Yani that means the magnetic monopole does not exist. So always the dipole exists in the magnetic dipole exists just like a south pole and north pole. And the third equation is del cross E is equal to 0 for a static field. So this equation is also known in static field, but in the non-static field, so this equation is equal to the del cross is equal to minus del B over del T, where B is the magnetic flux density. So in the non-static field, which one is del cross is equal to minus del B over del T, but in the static field, that means it does not change the magnetic flux density with respect to the time. So that means the del cross E is equal to 0. So this means this is irrotational vector. So that means the curl of that particular electric field should be 0. So this is the conservation of the electric field. And the last one is the del cross H is equal to J. This equation is also known as the Ampere's circuital law. And if we convert it in the integral form, so H dot dl, which one is equal to J dot ds, where J is the electric current density, and H is the magnetic field intensity, and dl is the differential length that particular path. So by using these, so we know that the electric field, the relation between the electric field and the potential, which one is equal to electric field is equal to minus of gradient of vector. So in that particular same fashion, we have to discuss what is the magnetic scalar potential Vm and the magnetic vector potential A. So in this, if we compare this, so electric field intensity and the magnetic field intensity is to be similar here. So electric field intensity we have to be put here, and what is the magnetic field intensity H? This is minus, which was same gradient of that. This is the vector potential. So this is the Vm, also a magnetic vector potential. If J is equal to 0, that means the condition is that if the current density is 0, so that means that this equation is to be exist. So that means the H is equal to minus ka grad of magnetic potential. So magnetic scalar potential, or we can say. So that means that by using the J is equal to del cross H, by using the Ampere's circuital law, if we put it, this value H is equal to minus del of Vm here. So if we put the value of H is equal to minus del Vm, and we curl off that particular system, so we know that the identity of mathematics, that the curl of any gradient quantity should be 0. So we can say del cross del V, which is equal to 0. This is the mathematical identity. So that means that this is equal to 0. So J is equal to 0. When J is equal to 0, that means the current density should be 0. Then this equation, magnetic field intensity, which is equal to minus ka grad of magnetic potential Vm. So if we derive this equation, or we can say Vm is satisfied the Laplace equation for del square Vm is equal to 0. So this equation also verify the Laplace equation. And what is the magnetic flux from vector potential? So what is the meaning of this? So magnetic flux is equal to the B dot dl. That means the B is the magnetic flux density. So magnetic flux density in a specified surface which is equal to the total outward flux. So total outward magnetic flux, psi, which is equal to the what is the magnetic field density in a specified surface. So we also obtain the relation between the magnetic vector potential and magnetic flux density. So by using the theorem psi is equal to B dot ds, if we put B is equal to del cross A, so this equation is to be converted into the del cross A is equal to ds. So we put B is equal to del cross A. So that means the magnetic flux density which is equal to del cross A. That means this is the potential. This is the magnetic vector potential. So this is not a scalar potential. This is a magnetic vector potential A, which is defined with respect to the magnetic flux density, which is equal to the B is equal to del cross A. So we put B is equal to del cross A dot ds. So we apply a Stokes theorem in that particular system. So we know that by using the Stokes theorem, this surface integral is to be converted into the line integral. So del cross A dot ds, which is converted into the line integral, that means the along a closed path which is equal to the A dot ds. So we easily calculate कि psi is equal to the total outward flux and the relation between the magnetic vector potential which is equal to the A dot dl. So the magnetic flux density total outward flux which is equal to the B dot ds in terms of magnetic flux density and the magnetic vector potential. If we given magnetic vector potential, so we calculate the total magnetic total outward flux, which one is equal to the total magnetic outward flux which is equal to the A dot dl. So this is a very important formula to calculate the total outward flux in terms of magnetic vector potential. So we have taken one example regarding to calculate the magnetic flux density psi. So in this case, we have to be taking one example. Given the magnetic vector potential, A is defined that A is equal to minus rho square by 4 in the direction of AZ Weber per meter, and calculate the total magnetic flux crossing the surface psi is equal to pi by 2, where the rho is lies from 1 to 2 and the Z is lies from 0 to 5 meter. So first we calculate what is the total outward flux. So total outward flux psi is equal to B dot ds. So we also calculate the total outward flux is equal to B dot ds, or we also calculate the total outward flux by using the magnetic vector potential A dot dl. So in both ways we have to be calculate the total outward flux, and the value of the total outward flux is to be same. So first we choose the method 1. By using the method 1, we have to calculate the total outward flux. So the total outward flux, what is the meaning of this? So the total outward flux psi, which is equal to the B dot ds, where B is the magnetic flux density in a closed path. That means the ds is the closed path or closed surface area. So we know that B is equal to del cross A. So by using this system is a cylindrical system. So we can see that the component are rho, phi and z. So this system is a cylindrical system. So we compute del cross A by using the matrix form. So this del cross A, what is the value of this? So we solve the matrix then the value of B, which is equal to the minus del Az upon del rho in the direction of A phi. So in this question, A is given that minus rho square by 4 in the direction of Az. So we just partially differentiate this magnetic vector potential with respect to the rho. So if we differentiate this function with respect to the rho, so the value is minus 2 rho by 4. So that means that the value is minus rho by 2, and we multiply with minus 1, so minus is plus 1 in the direction of A phi. So the value is rho by 2 A phi. And what is the ds? Ds is the differential surface area. So differential surface area is a vector quantity. So in that direction, so we can see that the B dot ds, psi is equal to B dot ds. So B is the del cross A, and this A is defined in the Az direction, or we can say A phi direction. So ds also in A phi direction. What is the meaning of this? So in the A phi direction, the ds should be the d rho into dz. So in that particular direction, the differential surface area in a cylindrical system, which one is equal to the d rho into dz. So we put it this value in that particular system, or in that particular system, that means the B dot ds. So we easily calculate what is the value of V, rho by 2 in the direction of A phi. So ds also in A phi, because A phi dot A phi is equal to 1. So that means rho by 2 d rho dz, and the limit of rho lies from 1 to 2, which is given in that particular question, where rho lies from 1 to 2, or we can see that rho lies from 1 to 2. And dz, the limit is z is 0 to 5. So in this question you see that this is 0 point, so this height should be in the 5 direction. So that means z is equal to 0 plane and z is equal to 5 plane. So the limit of z is 0 to 5, and we calculate what is the value of this, the total outward flux, which one is equal to the 3.75 Weber. So we easily calculate by using the method 1, B psi is equal to B dot ds, the total magnetic flux, which one is equal to the 3.75 Weber. So we easily calculate by this, but by using the second method, we also calculate. What is the second method? If we calculate the psi with respect to the magnetic vector potential, so the value of magnetic flux density, so total outward magnetic flux, which one is equal to the A dot dl. So we know that the method 2 is where we have to be defined here. The total magnetic flux psi is equal to A dot dl. So that means this is the psi 1, this is psi 2, so psi 3, total outward flux, which one is equal to this, and psi 4. So the total outward flux density, which is psi, is equal to the psi 1 plus psi 2 plus psi 3 plus psi 4. So we know that psi 1 and psi 3 are 0, because psi 1, what is the psi 1? So no change in z direction, so that means this is z is constant. So that means in that case we not define this total outward flux in the Az direction. So we can say the psi 1 is equal to 0, and in psi 3 this is also a constant, because z is equal to 5. Z is not a variable, z is constant. So in that case, the psi 1 and psi 3 is equal to 0. But in the case of psi 2 and psi 4, z is varies, because this system is to be varies according to the Az direction. So the total outward flux now is the sum of psi 2 plus psi 4. So psi 2 is what is the meaning of psi 2? psi 2 is the this system. So the total outward flux, which one is equal to A dot dl. So A is defined that A is minus rho by 4 in the direction of AZ. So dl also defined in the AZ direction. What is the meaning of that? dl, which is equal to the A rho d rho A rho plus rho d phi A phi plus dz az. So the differential length in cylindrical coordinate system, which one is equal to the d rho A rho rho d phi A phi plus dz az, but A is defined in the AZ direction. A is defined in AZ direction. So because A is given in the AZ direction, in question we have to see that A is given that in the AZ direction, and the dl in cylindrical coordinate system, which one is here. So if we dot product is given that, so that means the AZ dot AZ should be 1. AZ dot AZ should be 1. So we choose dl is equal to dz az. So that means the for psi 2 case dz az in the direction of this, and we put what is the value of A. A is minus rho square by 4 az. So minus 1 by 4 is to be taking a common. Rho square for in that particular direction. For psi 2 case, the rho distance should be 1. So we put rho is equal to 1. So rho square, this is rho is equal to 1, rho square by 4, and z lies from 0 to 5. So we put the limit z is equal to 0 to 5 integral of dz. So we calculate the total outward flux psi 2 by using these integral, and we also calculate the psi 4 by using these calculation, because the rho is equal to 2 for this case. So rho is equal to 2 for this case, so that we put the rho is equal to 2 here. So this is the rho is equal to 2, and the limit is 5 to 0. So the direction of flux is, if we move here, so direction of this is here, and the z direction is 5, where z is equal to 0 is here. So the limit is 5 to 0 dz. So if we solve this equation, we find that the total outward flux, magnetic outward flux, which one is equal to 3.75 Weber. So both the cases, in both the method, by using the psi is equal to B dot ds or A dot dl, we calculate the total outward flux. And the next topic is force due to the magnetic field. This is also a very important point to find the what is the force. So due to the moving charge potential Q in the B field, the force on the current element in an external B field between the two current element, B is defined the force per unit current element. So in this case, we have to see that the stationary and the moving electrons is to be impart in a electric and magnetic field. Then analogous to electric field force, we know that if the charge is Q, which is placed in the electric field E, so the force on that particular charge, which one is equal to the Fe is equal to Q into E. We have magnetic force also. So the magnetic force having a charge having a velocity of u, which is placed in a magnetic flux density B. So the force on a charge Q, which one is equal to Q u cross B. So the total force on that particular charge which are moving in the electric field as well as the magnetic field, which one is equal to the F is equal to Fe plus Fm. So Fm is the perpendicular to the u and b, because u cross b, we know that what is the meaning of u cross b. Fm is equal to Q into u cross b. That means the what is the meaning of that? The force what is the magnitude? Magnitude is u cross b, and the direction is perpendicular to the u and b. If the charge moving has a mass m, then what is the force m? We know that F is equal to m into a. This is the Newton's law, where a is the acceleration. So acceleration we have to define in terms of the velocity, which one is equal to the du by dt. So if we put here, so what is the meaning of that? We know that what is the total force, which one is electric plus magnetic, which one is equal to QE plus U cross B. So we easily calculate what is the meaning of this. Usually the magnetic force, which one is less than the electric force. So the next question is, what is the forces on a current element? So if ideal current element and the charge q is here, so what is the force? So we can write here what is the force. We know that q is equal to F is equal to q u cross b, or we can say I into dl cross b. So for a closed path line where I is the current element, so the magnetic force, which also is equal to the I dl cross b in the direction of that particular area, or we can say ideal, this is perpendicular to the ideal current element and magnetic flux density. So we easily calculate what is the magnetic force ideal is cross by using the formula ideal cross B. If the charge sheet, if the charge is distributed on the surface, so this one is equal to the magnetic force is equal to K ds cross B, where surface K is equal to defined in the ampere per meter. When charge is distributed on the volumes per unit volume, so that means if J is the current density, so the magnetic force, which one is equal to J dV cross B. So how we calculate the force between the two current elements? So this is the first current element having a I dl1, I1 dl1, here I dl2, I2 dl2, current is to be flowing. So this is the current element 1, this is current element 2, this. So the distance between them is R21. So the total force F1 due to the current flowing that particular path, which one is equal to the mu naught I1 I2. So the product of how much current flow in the first path and how much current flow in the second path I1 I2 upon 4 pi integral L1, what is the length of this loop and what is the length of this loop, is L1. This one is L1 loop, this is one L2 loop. So we integrate 0 to L1, 0 to L2, and if we take in a differential element dl1 here and the dl2 differential element here, so we easily calculate the force F1 due to this circular path. So which one is equal to the dl1 cross dl2 in the direction of R21 upon R21 ka square, where AR21 is the unit vector and this AR21 is defined by R21 vector upon R21 mod. So if we replace this by this, so this R21 mod is equal to the R21 Q. And another questions which has to be asked by using some, I just given some question regarding this. So according to the this force, if your charge is placed in a electric field as well as the magnetic field density, so a charged particle moves with a uniform velocity 4 AX meter per second in a region where electric field is defined 20 AY volt per meter, and the magnetic flux density is defined B is equal to B naught Az Weber per meter square. Determine the B naught such that the velocity of the particle remains constant. So this is very important questions which has to be asked in the university exam. So in this case, we know that if the velocity of the particle remains constant, that means Fe is equal to minus Fm. That means the how much electric force which is equal to the, that means the Fm magnetic force which is equal to the 0, or we can say electric force which is equal to the minus Fm. So we know that what is the electric force? Electric force is equal to Q into E. What is the magnetic force? Q into U cross B. So they asked you your question कि if the your magnetic flux density in B naught and U is defined, U what is the velocity? So B is defined B naught Az. So we put B is equal to B naught Az and U is defined 4Ax. So this is the velocity. So this is 4Ax. So Q is cancel out and the electric field, which one is 20 AY. For AX cross B naught AZ. So what is the value of B naught? So we easily calculate. So B naught is equal to, you have to just see that this is 20 upon 4 is equal to minus 5. So we easily calculate the magnetic flux density B naught, which is equal to minus 5 in magnitude, and the direction is Az, or we can say the magnitude is 5 in the direction of minus Az direction. So we easily calculate this question, and this question is to be asked many times in UT examination. So this is the representation. If your charge, this is the charge particle having a velocity u and placed in electric field, so or as well as the magnetic field is defined here. So that means what is, this is magnetic flux density and this is the electric field. So electric field direction is from here to here, and the magnetic flux density defined inward this surface. So how much force is to be here, and what is the value of magnetic flux density B naught? The magnitude is 5 Weber per meter square. So next is magnetic boundary condition. So by using the Gauss law and the Ampere circuital law, we have to be define the boundary condition. So boundary condition is defined here, B dot ds is equal to 0. That means the magnetic monopole does not exist, and the H dot dl is equal to I. That means the in a loop, if the magnetic field intensity H, so in a closed path H dot dl, if we integrate them, which is equal to the I enclosed. So we have to define here this is region 1, this is region 1, and this is region 2. Here region 1 and 2 is defined, the permeability is mu1 and here is mu2, and the B is the magnetic flux density B1, where the horizontal tangential vector is B1t and the normal vector is B1n, and the direction of in second medium B2 is the magnetic flux density in the region 2, and the tangential vector is B2t and the normal vector is B2n. The permeability of region 1 is mu1 and second region is mu2, and in this case the total surface area delta S and the height is delta H. So we know that, so B dot ds is equal to 0, or in this case, in the region 1, B1 into, in the region 1 B1 into delta S minus B1n, or that means this one is B1n, this one is B2n. So B1n is the normal vector in normal magnetic flux density in region 1, normal magnetic flux density in region 2. That means the B1n delta S minus B2n delta S, which is equal to 0. So that means B1n is B2n, which one is equal to which are equal, or we can say this is continuous, or we can say the normal vector, normal magnetic flux density and the normal in the region 1, which one is equal to the normal magnetic flux density in the region 2. So we can say normal magnetic flux density are continuous in this case. Or we can say we have to be defined B is equal to mu1 mu r h1 and B2 is mu2 mu r into h2n. So the h1n upon h2n is equal to mu2 by mu1. So we consider this case for tangential electric field. So we can define here H dot dl to I k into delta w. K is the defined the magnetic current density, h1t into delta w, h1t into delta w. So we can say tangential vector is here, and the h1n, what is the length, h1n, which one is equal to delta h by 2, and this tangential vector in whole or in the region 1. So we can define here h2t delta w, and in the region 2 this is also we define delta h by 2 h2n, and h1n is also defined in delta h by 2. So we can say if delta h tending to 0, so this function is to be vanished. So we can say this function is vanished. So h1t minus h2t, which is equal to k. So k is the vector if no current at boundary. So the boundary current element, surface boundary current element. So if this k is equal to 0, so h1t is equal to h2t, or we can say the tangential magnetic field intensity is continuous. So here, so what is the two boundary condition? h1t is equal to ht2. So the tangential magnetic field intensity is equal, but the magnetic flux density in region 1 and region 2, which is equal to the bn1 upon bn2. That means the bn1 is equal to bn2. That means mu1 hn1 is equal to mu2 hn2. That means hn1 upon hn2, which is equal to mu2 by mu1. So these two boundary conditions we have to be asked, or in the university examination, ki what are the two boundary conditions associated with magnetic field. So that means the normal magnetic field intensity in region 1 upon normal magnetic field intensity in region 2, which is equal to the permeability of region 2 upon permeability of region 1, and the tangential magnetic field intensity in region 1, h1t and h2t is equal to, which are continuous, or we can say h1t is equal to minus h2 is equal to this. Thank you. So in this lecture we have to be covered what is the magnetic boundary condition, what is scalar vector potential, what is magnetic vector potential, and how we solve these questions. So thank you very much.